Every day, millions of people cross bridges without thinking twice. You drive over them, you walk across them, you trust them with your life. But here is the uncomfortable truth. Some of those bridges are far more vulnerable than you think. And one bridge in particular became so unpredictable, so dangerous, that it changed engineering forever. Because it did not collapse under weight, it did not collapse because it was overloaded, it collapsed because of something you cannot even see: wind. This is the story of the Tacoma Narrows Bridge, a bridge so elegant, so modern for its time, that people admired it from the moment it opened. They even gave it a nickname, Galloping Gertie. But just months after it was built, something strange started happening. The bridge began to move, not slightly, not safely, violently. Back in 1940, the Tacoma Narrows Bridge was seen as a symbol of progress. Engineers were pushing boundaries, designing longer and lighter suspension bridges. The goal was simple: use less material, reduce cost, and still maintain strength. And on paper, it worked perfectly. The bridge stretched beautifully across the water. It looked stable, it looked efficient, it looked like the future. But there was one problem. They did not fully understand how wind interacts with flexible structures. Almost immediately after the bridge opened, people began to notice something unusual. The roadway did not stay still. It moved in waves. Cars driving across the bridge would rise and fall as if they were traveling over water. Some drivers even stopped in fear because the motion was so unsettling. Imagine driving on a bridge that behaves like an ocean. That is not normal. But instead of shutting it down, engineers tried to manage the movement. They believed the oscillations were not dangerous. They thought it was just a minor design issue. What they did not realize was that the bridge was slowly building up energy. Then came November 7th, 1940. The wind speed that day was around 40 miles per hour. Not a storm, not extreme weather, just a steady wind. At first, the bridge began with its usual up and down motion. But then something changed. The movement became more aggressive. Instead of bouncing, the bridge started twisting. One side rose up while the other dropped down. Then it reversed over and over again. The entire structure was no longer just moving. It was rotating. This was something far more dangerous. This was aeroelastic flutter. At this point, the bridge had entered a feedback loop. The wind pushed the structure. The structure moved. That movement changed how the wind flowed around it. And that new airflow pushed the bridge even harder. More movement created more force. More force created more movement. And it kept building. Drivers abandoned their cars. People ran for safety. The bridge was completely out of control. Then, piece by piece, it began to fail. Steel cables snapped. Sections of the roadway tore apart. The massive structure could no longer hold itself together. And in a dramatic and terrifying sequence, the Tacoma Narrows Bridge collapsed into the water below. All of this happened not because it was weak, but because it behaved in a way engineers did not fully understand. That is what makes this story so unsettling. The bridge was not poorly built. It was not overloaded. It was not neglected. It failed because of physics that had not yet been fully accounted for. At the time, aeroelastic flutter was not well studied in large structures. Engineers focused heavily on strength and weight. They designed for gravity. They designed for load, but they did not fully design for movement. And that mistake changed everything. After the collapse, engineers around the world began to rethink how they design bridges. Wind tunnel testing became essential. Aerodynamics became a critical part of structural engineering. Modern bridges are no longer just built to be strong. They are built to behave correctly under dynamic forces. But here is the part that should make you think: the risk never completely disappears. Today's bridges are safer, smarter, and far more advanced, but they still face the same invisible forces: wind, vibrations, resonance. Every structure interacts with its environment, and if that interaction is misunderstood, failure is always a possibility. Every time you cross a bridge, you are trusting more than just concrete and steel. You are trusting calculations, assumptions, and models created by engineers. Most of the time, those models are accurate, but the Tacoma Narrows Bridge taught the world a brutal lesson. Nature does not follow your expectations. If you misunderstand the system, it will expose you. That is why engineers are not afraid of bridges, because they fail often. They are cautious because when failure happens, it is usually something no one fully anticipated. Subscribe to Engineered Reality, where we break down the hidden engineering failures shaping the world you live in.